So today we're going to look at chapter 3, which deals with some important topics such as radiation and how it relates to the atomic structure. Okay, so let's move on to talking about a brief history as to how we arrive at our current understanding of the atomic structure of atoms or elements. So this is just a flow chart which gives you a brief history of what we call the atomic theory. The first persons to come up with this whole notion of subdividing matter into its smallest units were the Greeks, at least on record. And then early chemists performed experiments, and their experiments led to Dalton coming up with his atomic theory. Let me expand this here. Okay, so after that, some limitations were discovered concerning his model, Dalton's model, and this led to scientists in the early 20th century to basically come up with experiments that modified to a great extent the model that Dalton put forward. So people like Thomson and Rutherford were involved in that effort. And then after their discoveries, and as a result of their discoveries, the new models that is used to explain the nature of the atom, there were still some issues, right? There were still some limitations with these models, and therefore more modern theories were put forward and worked on in order to get to the heart of what the true nature of the atom is. Now, before we get into the atom itself, we need to spend some time talking about radiation, electromagnetic radiation. Now, electromagnetic radiation is basically a form of energy, right? There are three ways that energies can be transmitted from one object to another. You have conduction and you have convection, which I won't get into, and then you have what is known as electromagnetic radiation. And the thing about this form of way of conducting or allowing electrons, I should say energy, to get from one object or one region to another is that unlike conduction and convection, electromagnetic radiation as a form of energy can travel through space, right? Convection and conduction require some material medium, but in the case of electromagnetic radiation, it can travel through a vacuum. And that's basically, for example, how the energy from the sun gets to Earth, right? Because space is a vacuum, and the energy in the form of heat and light is transmitted from the sun to the Earth, and that's how we get the energy from the sun. So what we're going to look at here are different forms of energy, and we're going to talk about these in more detail in terms of their frequency and wavelengths. All those terms I'm going to define shortly, right? But here are just some examples of different forms of electromagnetic radiation. You have the light from the sun, you have X-rays, you have microwaves, you have radio waves, television waves, which is basically the same thing as radio waves, and radiant heat. All right, so these are all forms of energy. And what they all have in common is that they show wave-like behavior. All right, so all these forms of radiation display wave-like behavior, and at this level I won't go into the details as to the nature of the components of the wave-like behavior. For all purposes, we're just going to assume that to be the case, right? There's evidence actually to support this, but I won't get into that right now. That's for General Chemistry 1. So another thing that they all have in common is that they all have the same speed in vacuum, and that speed is 3.00 times 10 to the 8 meters per second. That is true for every form of electromagnetic radiation. All right? So what we're going to look at now is the characteristics of a wave, because if we understand this, then there's a lot of things that we can understand about radiation. So there are a couple of things that all waveforms have. The first of which we're going to discuss here is what is known as the wavelength. And you'll notice I have this symbol here. This is a Greek letter lambda, which is what we use conventionally to represent wavelength, right? Now, what is the wavelength of a waveform? Well, the wavelength is basically the distance between two successive peaks in a waveform. So here we have a waveform here, and we take the distance between one peak and another peak, and that will be the wavelength. Or correspondingly, we could take the difference between two troughs, right, which would be the minimum point of the waveform, So if you take the distance between here and here, that's a wavelength, all right? So that's basically the definition of a wavelength of a wave. And what you're going to find is that different forms of radiation have different values for the wavelength, all right? Another important characteristic of any waveform is what we call the frequency of the wave, all right? And here, the symbol that is typically used for the frequency is this Greek letter called nu. It looks like a V, but it's not quite. But that's the typical frequency symbol. In some textbooks, actually, I've seen they use the letter F. So if you prefer to use F to represent the frequency, that's fine by me, all right? So that's the frequency of the radiation or the waveform. And let's define what that is. The frequency of the of any particular waveform is the number of wavelengths that pass a particular point per second. All right. So if you concentrate on this waveform moving, and let's say you focus on one point right here, and you count the number of wavelengths that passes that particular point per second, then that would be the frequency. All right. So that's basically what the frequency is. Now, in terms of units, the frequency of any waveform is typically given in s to the minus 1, seconds to the minus 1, and there's a special name and symbol for that unit. It's called the Hertz unit, all right? And Hz would be the symbol for it. So when you see Hz, it's the same thing as seconds to the minus 1. So in textbooks, you'll see they use the s to the minus 1 or the Hz symbol. It's the same thing, all right? As far as wavelength is concerned, pretty much any unit of length can be used for the wavelength. You can have wavelengths expressed in micrometers or millimeters or centimeters or meters or kilometers. It all depends on, you know, the typical or the type of problem that is involved, all right? So the third characteristic of the wave, of any waveform, is known as the speed, right? And the speed is basically how fast the wave moves through space. Now, in the case of electromagnetic radiation, as we said before, the speed of the waveform, in fact, let me write this down here, for electromagnetic waves, the speed is equal to the speed of all forms of radiation, which is 3.00 times 10 to the 8 meters per second, right? Now, conventionally, we use c as the speed, representing the speed of all forms of electromagnetic radiation, right? So c would be equal to this right here. But this v here is for any form. But we use c for specifically electromagnetic radiation, all right? So that's the speed of the waveform. Whoops, let me get this taken care of here. Okay, so that's the speed of the waveform, right? So as you can see, there's a relationship between the speed of the waveform, the wavelength, and the frequency, right? And the units of the speed would be dependent on the units that you would use for the wavelength and frequency. Now, typically, let me go back to my pen function here. Typically, the wave, if you're using this equation here, typically the wavelength would be expressed in meters, and the frequency will be expressed in seconds to the minus 1 or hertz, which means that as a result, the velocity or the speed of the radiation or the waveform would be m s to the minus 1 or m slash s. It's the same thing, all right? And specifically, as we said before, as it relates to radiation, the speed of the radiation of the waveform is always going to be equal to 3.00 times 10 to the 8 meters per second, all right? So that's a relationship between the speed of a wave, the wavelength, and the frequency. Now, it turns out that radiation, such as the light that our eyes are sensitive to, also exhibits what we call, properties of a particle, right? And these light particles are called photons, all right? So therefore, we have basically the wave model and the particle model that can be used to explain different properties of light. So the point here is that there are some properties that can be explained using the wave model. There are other properties that can be explained using the particle model. So we call this a wave-particle duality, which I think I'll make mention of shortly. All right. Now let's talk about the electromagnetic spectrum. The electromagnetic spectrum is basically a listing of all forms of radiation according to either increasing wavelength or increasing frequency. All right. Now let me just say something here before I talk about the spectrum here. Going back to the equation I gave you earlier, remember I said that the speed of the radiation, which is c, the speed of light, is equal to lambda times nu, right? Now, because this is constant, what that means is that if lambda increases, then the frequency would decrease. Or if lambda decreases, the frequency would increase. So in other words, you have an inverse relationship between the wavelength and the frequency of the radiation. So if you look at this diagram right here, which basically gives you all the forms of radiation that exist in order of increasing wavelength, right? You'll see that the wavelength here is in meters, right? And you see that at the low end, the wavelength of gamma radiation is 10 to the minus 12 meters, and then you have X-rays, and then you have ultraviolet radiation, and then you'll notice that there's a narrow band between 4 times 10 to the minus 7 and 7 times 10 to the minus 7 meters. That is what we call the visible part of the spectrum. So we're referring to here the different colors of light that our eyes are sensitive, right? So it starts with violet down here, then indigo, and then you have red here, you have orange here, you have yellow here, you have green, you have blue, and then you have indigo and violet if you're going the other direction. All right. So that's basically the spectrum, the electromagnetic spectrum. All right. So our eyes as human beings are sensitive to all these different colors within this narrow range. We cannot pick up, using our sense of vision, the other forms of radiation that falls outside of that range. So basically, all these other forms of radiation are invisible to us, and we're going to need instruments to be able to identify and detect them. So after we get past the visible range, then you have the infrared, which is just outside the red region of the visible spectrum. Then we have microwave, and then we have the radio waves. All right, so that's basically the full electromagnetic spectrum of all the different forms of radiation that are in this particular table or chart, expressed or put in order for their increasing wavelength. And as I said before, there's an inverse relationship between the wavelength and frequency, as I said here, which means that going in the other direction, the frequency would increase. So what we're saying here, we're saying that in terms of frequency, let's say we compare ultraviolet to radio waves, ultraviolet would have a higher frequency compared to radio waves, for example, in addition to the fact that radio waves has a longer wavelength compared to ultraviolet radiation. Okay, so that's basically the visible spectrum. So let me stop here, and the next video we'll be dealing with how we relate this that we just discussed in terms of the electromagnetic radiation to the Bohr atom. All right, so until next time.